Last video on inverse functions before we get back into logarithms. This video is all about graphing inverse functions, and this is really where we really need to concentrate as far as getting ready to graph logarithms and stuff like that. The prereqs here are that you need to know about inverse functions, everything I've talked about so far, the concepts of what an inverse function is, inverse function notation, finding the inverse function equation. You should also know how to do base graph transformations, because that's going to probably sneak its way into this talk. We're going to start this example, or this talk, with a simple example. Graph the inverse of this function, f of x equals 12x minus 1. And this function should be familiar because we just talked about this function, or use this function, in the last lecture that I did. There's going to be a couple approaches. There's always a couple approaches to graphing the inverse of a function. You can either, if you're given the function explicitly, you can either, find the inverse, or you can graph the function and then use a very special technique to help you graph the inverse. But since I haven't shown you the technique yet, obviously what we're going to do is find the inverse function for this function here, and then we'll go ahead and graph it. So to find the inverse function, we're going to let y equal 12x minus 1. And then we're going to solve for x. So and solve for x here. So when I do that, I'll get the following: y plus 1 over 12 is equal to x. Now technically, that's my inverse function. That implies that f inverse of y is equal to y plus 1 over 12. And I told you in my last lecture that I appreciate and really like this form of the inverse function, except in one case. And that one case is when you're asked to graph. When you're asked to graph, you should swap this variable out. Call it a different letter. In fact, call it x. And the reason why is because when we're graphing, we like to use our inputs along the x-axis and our outputs along the y-axis. So in this case, I'm going to go ahead and just call my inputs the letter x, and just tell you right now, this is not the same x as this one up here. It's not the same one. It's just, that's what's so confusing about it. By the way, this can be written as x over 12 plus 1 over 12, if you wanted to write it that way, which I do. And let's go ahead and graph this function. And there's a couple ways you could do it. You could just graph it. Actually, now that I'm thinking about it, there's three ways to graph the inverse of this function. I could use the fact that this is in y equals mx plus b form, 1/12 x plus 1/12. So the slope, this is a line with slope 1/12 and y-intercept of 1/12. I could do that, or I could build a table of values. That's another way I could do it. So if I want to build a table of values, looking at this f inverse function, I'll probably pick smart values for x, like x equals, let's do x equals 11. 11 plus 1 is 12. 12 divided by 12 is just 1. And remember, since this is a line, I only need 2 points. So let me do a negative value for x as well. Let's do x equals a negative 1. Negative 1 plus 1 is 0. So there we go. All right. So these are my 2 points, and I'll go ahead and graph that. Plot those 2 points and graph that line. What I get is this line right here, very shallow line. Now what I'm going to demonstrate next is I'm going to use the original function. So this is f inverse of x here. I'm going to go ahead and plot f of x. Now to show you what f of x was just 12x minus 1. So it's a slope of 12 and a y-intercept of negative 1. So let me go ahead and plot the y-intercept of negative 1, and then the slope is 12, so I'll go up 12 and over 1. 1, 2, 3, 4, 5. Oh, this is going to go off the screen. Now, I don't know if you can see it, but I've already plotted, like I said, the y-intercept of 0, -1. I've shifted the graph down here so that I can make more room. But the other point is 1, 11. I rose 12, went over 1, but if you rise 12 from a height of -1, then you go up to a height of 11 and then over 1. Notice something about these x and y values. Look at this. The x value here is -1, the y value is 0. And look at here. They're swapped. Look at this here. X value is 1, y value is 11. And here, they're swapped. Of course, because they're inverse functions, so the x and y values play opposite roles. They're swapped in this case. Let me go ahead and draw the line in. And so that is the line for f of x. That's the graph of f of x. There's something I want you to notice about that. Since all the x and y values are swapping across those two lines, that means that it should be a reflection about the line y equals x. And if you look at these two graphs, the red graph and the black graph, they sure are. They're an absolute reflection about the line y equals x. And it's because once you're about that line, if you consider the world around that line y equals x, well, that's where y is the same thing as x. But on, let's say, right here, this point, its x and y values are opposite the x and y values there. In fact, let's see, that's 1, 2, 3, 4, 5, 6, 7, 8. That's x equals 8, y equals 1, 2, 3, 4, 5, 6. And this point here is actually, since it's 2 back, it's x equals 6. And, well, I must have counted wrong. No, wasn't that I counted wrong. It's that I put the point in the wrong spot. This is the mirror image right there. Anyway, it's 2 back, that's x value 6, and 2 up. So we were at a height of 6, we're now at a height of 8. See, these two are mirror images about this line y equals x here, and their x and y values have been swapped. That is true for every point on the coordinate plane. Pick any point that you want and pick its mirror image on the opposite side of y equals x. They will have opposing x and y values. I keep graphing the wrong one there, but twice actually. So for example, this point right here is x equals 2, y equals a -2. This point right here is x equals a -2, y equals 2. And they're mirror images about this blue line. Okay, so it turns out that the graph of f inverse is just the graph of f being reflected about the line y equals x. Now let's do a simple example that doesn't involve an actual given function. Let's just say somebody comes up and gives you the graph of a function. Suppose somebody came along and told me this is the graph of my function f. Now what I want to do is graph the line y equals x. So this is y equals x, and if you probably notice, I just readjusted that curve because I kind of did it incorrectly. But anyway, so the black curve is some function f of x, and then I go ahead and graph y equals x. Now if I want just a quick and dirty graph of this, of the inverse, and I'm not really concerned about being super exact, I'll go ahead and just maybe choose a different color because it'll get kind of confusing if I don't. And it's going to be the mirror image about this red line. So in other words, like over here, it's going to do something like this. It's going to do this. I want to come bow back in a little bit here. I know I'm doing a kind of a messy job, but it gets the point across, right? Goes back around here. Not the best again. Kind of a little messy. Oh well. And something like that. So the blue curve is something like the inverse function. And that's a quick and dirty way of graphing the inverse function. It's really just a very nice way to do things, because the fact is that, you know, whatever xy value this point has, you swap them, it'll actually be right here for the inverse function. So very nice way to plot these. But that leads us to a kind of an interesting example as well. Let's go ahead and graph f of x equals x squared. So when x is 1, the output's 1. When x is 2, the output's 4. And when x is 3, the output is 9 up here. So I'll just, same thing with when x is -1, y is 1. When x is -2, y is 4. And when x is -3, y is 9. And then we go ahead and connect the dots, right? What's going to be interesting about this, and I'm going to go ahead and label those points, is when you watch the last lecture on determining whether something's a function or not, or actually I think the last lecture I did was on function notation, but I've talked about how to determine whether a function is invertible or not. And I have mentioned that when you have an even power, it generally means the function's not invertible. And here's why. This function goes through 0, 0. It also goes through 1, 1. It goes through 2, 4, and 3, 9. So its inverse, I'll do that in blue, should go through 0, 0, 1, 1, 4, 2, 1, 2, 3, 4, 2, and 9, 3, 5, 6, 7, 8, 9, up 3. So it should start to look something like this. Again, kind of freehand drawing this. Actually, it would be above this red curve in this area, but it doesn't matter. Okay. So, and let me label those points. That's 9, 3, and this is 4, 2. But remember, for this parabola, there's also these values over here. X equals the -1. That's not how you spell -1. Y equals 1. X equals a -2, y equals 4. And x equals a -3, y equals 9. So let me plot the opposites of those points. So in other words, swap the x and y values. So for this first point here, swap them. I'll plot x equals 1, y equals -1. X equals 1, y equals -1 is right there. So 1, -1. And then 4, 2, -2. So 1, 2, 3, 4, -2 is right here. You can already kind of see the shape. And then 9, -3. 9, 1, 2, 3 down. You can see the shape. It's going to be a parabola. It definitely is a parabola, but it's on its side. I'll finish this out really quickly. And the question is that a function? Is that blue curve a function? And the answer is no. It doesn't pass the vertical line test, right? So that means f was not invertible, or not 1-to-1. Is there an easy way to determine whether a function is not invertible? Well, if you have the graph of a function, it's super easy. All you want to say, you know a function's invertible if when you, how do I say this? If every y value, like this y value right here, leads to only one x value. Okay, so notice this height right here hits the graph only once. This height right here hits the graph only once, and so on and so forth. So in reality, to test whether a function passes or is invertible, you draw a horizontal line. If that horizontal line, if any horizontal line you draw hits the graph more than once, it is not invertible. Because what happens when you take the inverse is that, well, your domain and range swap. And that means that if you have two different x values that lead to the same output, well, when you try to find the inverse, like in this case, you have one input that leads to two different outputs. That's a bad thing. So let's go ahead and write that down as a theorem. It's the horizontal line test. Just like to find out if you have a function, if a graph represents a function, you usually do the vertical line test. Well, if you know that your graph represents a function and you want to know if it's invertible, do the horizontal line test. A function is one-to-one or invertible if every horizontal line intersects the graph of the function at most once. And so at this point, I could just draw up a quick few examples like this. This here is a function, don't get me wrong, this is a function f, but the fact is it doesn't pass the horizontal line, so while it's a function, it's not invertible. Notice that each input leads to its own output, right? All these inputs lead to outputs. However, the output of whatever height this is leads to 3 different inputs, and so that means that when we try to find the inverse, we'll not have a function. This guy right here, that's a function f, and it does have an inverse because every single horizontal line I draw crosses the graph at most once. So there you go. It's pretty much just that easy. Most students find this topic to be pretty straightforward. Now the last little bit that I want to talk about is more of a recollection of why I complain about the current function notation. So let me give you a simple example. Now remember, we write f of x, let's say f of x is equal to 1999 plus 0.25x. Okay. Whenever we find the inverse, I like it written as f inverse of y is equal to. Okay, and in this case it would be actually y minus 1999 over 0.25, and I don't know if you can see that. That might be at the top of your page. I'm not 100% sure, but it doesn't matter. I'm going to do it again. But just to let you know that most textbooks insist that that be written as f inverse of x. They insist on swapping variables. And as we've seen in this lecture, it's really useful to swap variables when you want a graph. But otherwise, it's pretty useless, especially in applications. So suppose that you rent a U-Haul, and I've given this application way back early in my lecture series, but suppose you rent a U-Haul and it costs $19.99 plus 25 cents a mile. Oops, I think in math, so 25 cents per mile. So therefore, if you want to create a cost function in terms of the number of miles that you've driven, it would be $19.99 plus 25 cents per mile. You plug in the number of miles you've driven, you get out the cost, right? That makes sense. Let's find the inverse of this function. So I'm going to use the letter C to represent my function, actually. So C is equal to 1999 plus 0.25 m. This whole business where f of x is always equal to y, that's BS. You could choose any letter you want, honestly. So let's solve this for m. Subtract 1999 from both sides, and then divide both sides by 0.25. And you will get that m is equal to that business right there. And in fact, that's the inverse function, right? Because we just have found the inverse. This tells me that, well, C inverse of C is equal to C minus 1999 over 0.25. And I know that C inverse is supposed to be the input value. Now, because I use the same letter, it'll look kind of confusing, but don't think these, well, don't let it confuse you. The fact is, the inverse function, we're going to plug in a cost. And I'm going to see how many miles, my output is the number of miles that I could drive based on that cost. If I were to, in a application, swap variables and change this back into C inverse of m is equal to m minus 1999 over 0.25, what the heck does that m stand for? If you think miles, no, it doesn't, because we swapped variables. That now equals the cost. And that's what's wrong with swapping variables, is that you start mixing up these letters. It's really horrible. Horrible, horrible, horrible. God, can you determine that I hate this? Okay. That's enough for inverse functions. It's just a really kind of a brief overview, although it wasn't too brief. But I will focus on them as we go into logarithms, more on logarithms, because we need more practice on them, especially on graphing.